Today we shall discuss few problems related to hydrogen atom, hydrogen-like atoms. Firstly, let the ground state wave function phi 0 or phi z of an electron in hydrogen-like atom be given by r by a 0, the ground state wave function. Wave function is this, where a0 is the Bohr radius. The problem is to normalize this wave function. Remember that the electron around the nucleus in an atom moves in three-dimensional space. So the normalization condition reads as psi star psi, so psi r dv integrated over all space to be 1. In this case, the wave function depends only on the radial coordinate r. So we write it as a modulus square from where dv in spherical polar coordinate is r square dr times d omega. So this is e to the power minus twice r a naught r square dr, r is equal to 0 to infinity times d omega over all solid angle. This is equal to 4 pi. So the result is 4 pi a modulus square times this one. We can write it as e to the power minus u square du from 0 to infinity, where u is equal to 2 r by a naught. So there will be a naught by 2 whole cube factor, and this part is gamma 3, which is equal to factorial 2. So the normalization constant can be evaluated from this condition. The thing to be remembered is that it is a three-dimensional problem. Once you normalize this, you can find out the expectation value of r in this ground state, expectation value of r in ground state, which is defined as psi g star r psi g dv, and the integration can be carried out in this fashion. Only factor is that this part will be cubed. So this will be 4 and this is factorial 3. We can calculate the expectation value of 1 by r also in this state. In this case, this power will be 1 and this will be factorial 1. And other related quantities can be calculated for this state. Another thing is that sometimes students are asked to find out the energy corresponding to this state. If you want to find out energy corresponding to this state, we recall that this is the total wave function, that is total. This is the total wave function. So psi g, it is the total wave function, so it is comprising of radial wave function times ylm function, which is for the ground state is y00, and this radial wave function can be written as r can be written as RNL, recall that radial wave function RNL of r can be written as UNL of r by r, and the requirement is that UNL is 0. So the corresponding UNL, this gives you the corresponding UG, the reduced radial wave function is some constant A r e to the power r by a0, and this u function satisfies this differential equation. Plus V effective is in this case is minus Z e square by 4 pi epsilon 0 r plus L into L plus 1 H line square twice mu r square. This is U N L is equal to E N L of. So the fact is that we need to differentiate this, and for ground state which for ground state becomes this is the ground state energy. Now the task is to differentiate this twice and to differentiate this equation twice. So del E dug dr is equal to A. This is the factor. First term is when we differentiate it to 1 minus r by a0 to the power minus r by a0, and the second derivative comes out to be first we differentiate this one with respect to r, so this is minus 1 upon a0 minus 1 by a0 1 minus r upon a0, and on simplifying this becomes r by a0 square minus twice a0 e to the power r by a0. If we substitute this in this equation, we find that minus h line square by twice mu, then this part is common in all the terms, so we can neglect this part. So it becomes r by a0 square minus 2 by a0. This is from this term. For UG, we write this part. So when we write epsilon 0, this 1 by r factor is getting cancelled with this. Now, if we as this is the final form. If we consider that this relation be valid for all values of r, then the coefficient of r on both the sides will be equal. That is, we find that minus h line square by twice mu a0 square with a minus sign is equal to Eg. This is the energy, ground state energy. And if we consider the term which is independent of r, if we equate the term independent of r, then we get h line square, 2 cancels out, mu a0 is equal to, this is plus sign, this is minus sign, we take it on the other side, z is square 4 pi epsilon 0, which gives you the expression for first bore radius. This gives you a0 to be this is the first bore radius, and there is no term on the right hand side or in this which has 1 by r dependence. So this gives you that L is equal to 0. So this part we have obtained by comparing the coefficient of r. This part we have obtained by comparing the coefficient which is independent of r, and this is obtained from the coefficient that goes as 1 by r. So this is very instructive example. Another problem is that consider the atom to be in this state, and this is the expression. Now our task is to identify classically forbidden region. Classically forbidden region means it is a region where the kinetic energy is negative. In terms of quantum mechanics, the expectation value of kinetic energy operated is governed by the wave function in a state NLM minus h line square by twice mu plus square phi NLM. This is the kind of expectation value. When the particle, and this can be written as minus h line square this is the radial part plus L square operator by twice mu r square. This is, and when the particle is in ground state, this part goes to 0. So the expectation value of kinetic energy operator in the ground state comes out to be twice mu, then this and since this is a psi g, and then it is 4 pi r square dr, and this is to be integrated from 0 to infinity. Now psi g is governed by this expression, and so Now we have psi g is equal to a e to the power r by a 0. So and if we substitute this, we get this minus sign, and this minus sign makes it plus h line square upon 2 mu. Then there is one a, and this is a modulus square, which is essentially a positive quantity. We have for this e to the power minus r by a naught 1 by r square, and this r square cancels out, so there will be a 4 pi factor. This r square and this r square cancels out, then this is r ddr of r square upon a0, r square upon a0 operating on r by a0 dr. It will be better to calculate this part. D psi g dr is equal to minus capital A by a0 e to the power r by a0. Now we come to consider this term ddr of r square this is equal to minus a by a0 then ddr of r square e to the power r by a0. This is equal to minus a by a0. When we differentiate it, this is twice r, and when we differentiate this one, it is r square by a0 e to the power r by a0. So if we apply the entire thing, first thing is minus h line square by twice mu, this part. Then from this part it is a star e to the power r upon a0. This 1 by r square gets cancelled, and this 4 pi is taken out of the integration. And for this part we write, this makes it plus, and dr. Now the kinetic energy, other parts are positive. So kinetic energy part is this, the sign of the kinetic energy operator depends on this. If this part is negative, then the kinetic energy is negative, and the particle is in a classically forbidden region. So for classically forbidden region, one must have this part is negative, that is twice r minus r square by a0 must be less than 0, or r is greater than twice a0. So for the ground state electron in hydrogen atom, for r greater than twice a0, the kinetic energy is negative, and the this positivity. Remember that the radial probability density is non-zero even for this state. Consider an hydrogenic electron which is in a superposition of state which is given by this. This state, for this covalent state, L is equal to 0, M is equal to 0. For this case also L is equal to 0, M is equal to 0. For this state L is equal to 1, M is equal to 2. 2p1 states. The wave function is already normalized. The wave function is already normalized, and we are to find out the value of expectation value of L square and Lz. We know that whenever we consider a state in NLM, a hydrogenic electron, then L square operating on psi NLM gives you L into L plus 1 H line square psi NLM, and Lz operating on psi NLM gives you MH cross psi NLM. So when L square operates on this superposition of state, in this case L is equal to 0, so 2 into 0 minus 3 into 0, and for this state it is 1 into L is 1, so it is 1 2 H line square by root 14. This is the result. And when this is 0, this is 0, this is 2 H line square by root 14, and Lz operating on this. For this M is 0, it is 0, so this is M is 1, so H line by root 14. It is the value of Lz, and if we want to calculate the expectation value, then we must integrate it by psi star from the left and integrate. We are to Now we come to the another problem. We know that the hydrogenic wave function comprising of two parts. One is the angular part, another one is the radial part, and the angular and radial parts are normalized separately. We shall consider few examples to show that the wave functions are, or the radial wave functions are indeed orthonormal. We know the radial wave function is this, and the normalization condition for the radial wave function means that R n prime L prime of R n L of R square dr integrated from 0 to infinity is equal to delta n prime delta L prime. Now let us check this relation for this combination. So integration from 0 to infinity R1s square R square dr. We assume that z is equal to 1, so this part is 2 1 upon a0 cubed from this part, and within it is r square e to the power, this r is missing, z is equal to dr from 0 to infinity. So this is 2 by a0 cube, and this part is e to the power minus u square du, where u is equal to 2r upon a0. So we have to adjust a0 by 2 to the power cubed, and this part is gamma 3 is equal to factorial 2 is equal to 2, and I have made a mistake. This term should be square, so this is 4 times. So the result is this a0 cancels out, this is 8 and this is 4 and 2, and the result is 1. Now r1s, r2s, r squared dr. This is a factor 4, and this is 1 by a cube, 1 by a0, that is 2 by a0 square to the power 3 by 2. This factor 1 by a0, and this is 1 by a0 square factorial 2, and then within it is 1 minus r by 2 a0 r square e to the power, this part is r e to the power minus r by a0 times e to the power minus r by 2a0. So it is equal to e to the power minus 3r by 2a0. And if we introduce a variable u is equal to 3r by 2a0, and we can calculate it to show that this is equal to indeed 0. This is left as homework. Carry out the integration using delta function, and when we use r2s, both for 2s, the result is 1. Similarly, we can use this wave function as well for the verification of this orthonormality of the radial wave function. The last problem that I am going to consider is a problem related to the radial probability, angular probability density. In the earlier lecture, we have defined the angular probability density PLM of theta is equal to YLM of theta phi modulus square. So this is the angular probability density. When an electron moves in a hydrogen-like atom problem, the potential is a spherically symmetric potential. That is, the potential doesn't have any angular dependence. Then it is expected that the angular probability density, which is already independent of phi, should not also have theta dependence. But if we recall our calculation in the earlier class, we found that P10 of theta is equal to Y10 modulus square. This is 3 upon 4 pi cos square theta. P11 of theta is equal to Y11. This is 3 upon 8 pi sine square theta, and this is also P1 minus 1. So if we consider the total probability for a given value of L, so this is P10 plus P11 plus P1 minus 1. This is 3 upon 4 pi times cos square theta, and if we combine these two, this is 3 upon 4 pi sine square theta, and the result is 3 upon 4 pi, which is independent of theta as we expected. These are the few typical problems related to the hydrogen-like atom problems, and by this lecture we end our discussion on hydrogen-like atom problems.